बिस्मिल्लाहिर्रहमानिर्रहीम। वेलकम बैक टू मैथमेटिकल मेथड्स ऑफ फिजिक्स। आज हम इसका लेक्चर नंबर 23 करेंगे। बिफोर स्टार्टिंग दिस लेक्चर, लेट्स सी व्हाट वी हैव स्टडीड इन द लास्ट लेक्चर. So review of the last lecture, we studied Fourier transform. So we studied Fourier transform in the last lecture. We defined Fourier transform and its inverse, and then we found out some Fourier transforms of some elementary functions. Then we went on to study Fourier sine and cosine transforms. Those were very similar to the Fourier transform, only exponential term getting replaced by sine and cosine terms. Then inverse Fourier transform, and we did some examples of finding Fourier transform and finding inverse Fourier transform. All right. So we will be continuing with the Fourier transform in today's lecture, and we will try to implement Fourier transform to solve partial differential equation, as in the case of Laplace transformations. So today, properties of Fourier transform, convolution theorem, solution of partial differential equation using Fourier transform. All right, let's start today's lecture then. Properties of Fourier transform. First of all, as in the case with Laplace transformations, Fourier transformations are also linear. All right. What do we mean by linear transformation? That if you take the Fourier transform of the linear combinations of fx and gx, then it will be a linear combination of Fourier transforms of fx and gx. So you can take the Fourier transform of fx directly and gx, and then you can multiply by c1, c2 and add them up. Similarly, Fourier inverse transform is also linear. All right. Change of scale. If f alpha is the Fourier transform of fx, then the Fourier transform of f ax is 1 over a f of alpha by a. So what do we mean here is, if you scale your variable x to a times x, it's a scaling, right? Then your Fourier transform gets scaled by 1 over alpha, and your x also scaled by 1 over alpha. You see, x, your argument alpha is replaced by alpha by a, and your total Fourier transform is also multiplied by 1 over a. All right. Then there is a shifting property. If f alpha is the Fourier transform of f of x, then the Fourier transform of fx minus a is, the Fourier transform of x minus a is e to the iota alpha a Fourier transform of f of x. So here is a shifting property. If you shift your origin from x 0 to a, x minus a, then your Fourier transform gets multiplied by e to the iota alpha a. Modulation property. If f alpha is the Fourier transform of fx, then the Fourier transform of fx cosine alpha x is this. You see, this is the mean value of alpha minus a and alpha plus a. You see, alpha minus a plus alpha plus a divided by 2 is the mean value of f alpha minus a and f alpha plus a. So if you just multiply your function by cosine alpha x, all right, your Fourier transform of the whole function, the resulting function, is the mean value of these two functions. Then there is a differentiation property. It's again little different from Laplace transform. If you take the Laplace transform of the derivative, it gives you s to the power r times the Laplace transform and minus all the initial values. Here you don't need initial values. Here you see, you are just getting the first part only. All right, that f of f rx, rth derivative, then you take the rth power of e to the iota alpha, negative iota alpha to the power r, and you just take the Laplace Fourier transform of f. There is no minus sr minus 1, f at 0 and f prime at 0 and so on. You are not using those values. Provided f and its derivatives are absolutely integrable. In addition, we assume that fx and its first r minus 1 derivatives vanish as x goes to plus minus infinity. So this is your property of the derivative. Let's see an example. Find the Fourier transform of partial nu by partial xn of the function uxt, assuming that u and its first n minus 1 derivatives with respect to x vanish as x goes to plus minus infinity. Now it's very easy, because see, the derivative is with respect to x, right? Because you have function fx, so derivatives are with respect to x. So this derivative with respect to x will give you minus iota alpha to the power n and the Fourier transform of uxt. That's it. All right. And what will be the Fourier transform of the second one? Because this is the derivative with respect to time, so this derivative comes out. You just take the derivative of the Fourier transform of u. That's it. You won't use this formula for the t derivative, because it's just partial by partial t of f of uxt. All right. So let's do this one. Also find the sine and cosine Fourier transforms of partial to u by partial x square. Here, this is the regular transform, not the Fourier transform. All right. So for the Fourier sine and cosine transform, we need to use integration by parts twice to get the answer. So let's do that. First, it was the Fourier transform of partial nu by partial xn. So this will become minus iota alpha power n and Fourier transform of u. All right. So this is whatever you want to write. If you want to write this as capital U, then it is capital U alpha t, because x goes to alpha. To be more precise, I can write this xt and it will convert x to alpha. So x becomes alpha, the Fourier transform is capital U. All right, so this is what you will get. And the Fourier transform of partial u by partial t will be equal to partial by partial t of Fourier transform of uxt. Because this is not the derivative with respect to alpha. So this is the partial u by partial t of alpha t. All right, so this is just the derivative of the Fourier transform. Then we needed Fourier sine transform of partial 2u by partial x square. All right, this is what we need. So this is square root of 2 by pi, 0 to infinity, partial 2u by partial x square times, it's a sine transform, so sine alpha x dx. This will convert this to alpha. All right. So integrating this by parts give me sine alpha x as it is. Integration of partial to u by partial x is partial u by partial x from 0 to infinity minus 0 to infinity. Derivative of sine is alpha cosine alpha x, and integration of partial to u is partial u by partial x dx. Now, as we had a condition that for second derivative, the condition is u and the first derivative will go to 0 as x goes to infinity, right? For this one, if you recall, we had the condition that the derivatives from first n minus 1 derivatives should vanish as x goes to infinity. First n minus 1 derivatives. So partial u, for partial n u by partial xn, first n minus 1 derivatives. So for partial 2u by partial x square, first derivative. U itself and the first derivative should vanish as x goes to infinity. So here partial u by partial x goes to 0 as x goes to infinity. All right. So it means at infinity this will go to 0, and at 0 sine is 0. When you replace 0, sine alpha 0 becomes 0. So from first we are not getting any contribution. This will become 0. And alpha comes out. So again, by using integration by parts, I can write this is minus 2 by pi alpha. Integration by parts gives you cosine alpha x as it is. Integral of partial u is u from 0 to infinity minus 0 to infinity. Derivative of cosine is minus alpha sine alpha x, and this is u dx. Now again, u goes to 0 as x goes to infinity. Right? So as x goes to infinity, this u will become 0, so this whole thing becomes 0. Minus when you take 0, then cosine alpha 0 is 1 and u at 0. So 0 minus cosine 0 is 1, u at 0t, plus alpha 0 to infinity, u sine alpha x dx. Alright, this is what you got. So this becomes 2 by pi alpha u0t and minus alpha square 2 by pi 0 to infinity u sine alpha x dx. Now this whole thing is the Fourier sine transform of u alpha, right? This is the Fourier sine transform of u. So what you got here is Fourier sine transform of partial 2u by partial x square as x goes to alpha is 2 by pi square root alpha u at 0t and minus alpha square Fourier sine transform of u alpha. So this is what you got, Fourier sine transform. Alright? So you see, this is the exact same part of the nth derivative, but this part is extra. This was not there. This was not there in the Fourier transform. Similarly, if you want to find Fourier cosine transform, what is the Fourier cosine transform of partial 2u by partial x square alpha? It is 2 by pi 0 to infinity partial 2u by partial x square cosine alpha x dx. Right? Again integrating twice by parts, cosine alpha x as it is, derivative, the integral of partial 2u is the partial 1 minus 0 to infinity, derivative of cosine is minus alpha sine alpha x and partial u by partial x dx. Alright, so 2 by pi cosine alpha x as x goes to infinity, partial u by partial x goes to 0, alright, and as x goes to 0, this will be minus cos alpha is 1 and partial u by partial x at x is equal to 0. This is what you will get. And plus alpha, again you can use integration by parts, so sine alpha x as it is, integral of partial u is u minus 0 to infinity, the derivative of sine is cosine alpha x and u dx. Alright, so from here you got, now as x goes to infinity, this u will be 0 and minus 0 will be 0. So you got minus 2 by pi partial u by partial x at x equal to 0 plus alpha times this is 0 and minus alpha comes out and inside thing becomes Fourier cosine transform of u alpha. Because if alpha comes out, this integral of cos alpha x u is the Fourier transform with square root of 2 pi as well. Of course, square root of 2 pi is being multiplied, right? Square root of, there was square root of 2 pi which is being multiplied from here, right? This goes here and from here it goes here. So 2 by pi is there and then it becomes cosine transform. So you got minus 2 by pi partial u by partial x at x is equal to 0 minus alpha square Fourier cosine of u alpha. So this is the Fourier cosine of partial 2u by partial x square with alpha. So if you are solving a partial differential equation with the help of Fourier transform, and the question is, which transform should we choose? Either Fourier sine or Fourier cosine transform. Then it depends. You see, Fourier sine transform uses the value of u at x is equal to 0. If this is given to you, then use Fourier sine transform. And Fourier cosine transform uses the derivative at x is equal to 0. If this boundary condition is given to you, you can use Fourier cosine transform. Alright, so depending upon the boundary conditions given, you can choose either sine or cosine transform to solve the partial differential equation. So, in case of sine transform, we require u xt at x is equal to 0. And in case of cosine transform, we require partial u by partial x at x is equal to 0. Alright? If this boundary condition is given, go for sine transform. If this boundary condition is given, then go for cosine transform. And you can solve the PDE. Alright, so we saw these two examples here. I did not prove it. Of course, if you can prove this property, it will be very easy. Here you need to integrate by parts, alright, and use induction. Every time you will be getting iota alpha outside. So you will be getting iota alpha to the power n at the end, minus iota alpha n, and you will be left with only u. One by one, all the derivatives will vanish. Alright, so similarly, which I did for sine and cosine, you have to use the integration by parts. You show it for 2-3 times, and then you can say, if I carry on in this manner, we will get minus iota alpha to the power n, and we will be left with only Fourier transform of u. All the derivatives will be gone. It's not difficult. I use that formula directly, but it can be proved very easily. Then Fourier transform of Dirac delta function. In Laplace transform of Dirac delta function was easy. It was exponential. And similarly, Fourier transform of Dirac delta function is Fourier transform of the Dirac delta function is also exponential type function. You see, Fourier transform of delta t minus alpha is 1 over square root of 2 pi, 0 minus infinity to infinity, e to the iota alpha t delta t minus a dt. Instead of x, we wrote t. If you want to write x, that's fine. Delta x minus a, you can replace, because t is a dummy variable on the right hand side. Alright? So now, you know the property of Dirac delta function. It picks up the value of your function, which is getting multiplied by the delta. It picks up that the value of that function at t is equal to a. So it will become iota alpha a. That's it. And 1 over square root of 2 pi is out there. So just by using the property of delta function, we arrived at the answer. When a is equal to 0, let's say if a is equal to 0, it will be just 1 over square root of 2 pi. There is no a here. A is 0. So Fourier transform of delta t is just 1 over square root of 2 pi. That is, the Fourier transform of the function delta t is constant and equal to 1 over square root of 2 pi. Similarly, Fourier transform of 1, if you take the inverse transform of 1, let's say this is a constant, right? It means if I take the Fourier transform of a constant, inverse transform of a constant, it will contain delta function, because delta function gives you a constant answer. So if you want to take the inverse transform of a constant, it will contain a delta function. So what you can do is you can multiply by square root of 2 pi, because it's linear. I know that 1 over square root of 2 pi has delta function, so it means 1 should have inverse equal to square root of 2 pi delta function. Alright, so I can find the inverse of 1, which is square root of 2 pi delta function. Then comes the convolution theorem. We did the convolution theorem for Laplace transformation. So let's see what it is for Fourier transform. So convolution theorem for Fourier transform. If f alpha and g alpha are the Fourier transforms of the function f of x and g of x respectively, then the product f alpha g alpha is the Fourier transform of the convolution f star g, which is defined as this. So it is again the same. the inverse Laplace transform of the product of two Laplace transform was a convolution. Similarly, Fourier inverse of the product is also the convolution. All right, convolution from minus infinity to infinity, fu g of x minus u du. So let's see the proof of this theorem. The Fourier transform of the above convolution integral yields, if I take the Fourier transform of the right hand side, let's say, Fourier transform of right hand side, it is 1 over square root of 2 pi minus infinity to infinity e to the iota alpha x, and then the function is this whole integration, right, which is minus infinity to infinity fu gx minus u du dx. 1 over 2 pi minus infinity to infinity, I can bring this e to the iota alpha x inside because this is the integral with respect to u. So I can bring x function inside. I got this one. Now since f and g are absolutely integrable, the order of integration can be interchanged. Why f and g are absolutely integrable? Because the Fourier transform of f and g exists, and it only exists if f and g are absolutely integrable. If they are not absolutely integrable, then their Fourier transform may not exist. All right. So if you change the order of integration, first comes x and then comes u. I brought x in and u out, so you got this thing. If I replace x minus u by another variable y, then dx is just dy. Therefore, this right hand side will become e to the iota alpha u, which comes out here. This will become e to the iota alpha y, and this is gy. And what is this? This is the Fourier transform of g. This is the Fourier transform of g. Once I write this as a Fourier transform of g, this whole thing, then this left hand side is Fourier transform of f. E to the iota alpha u is missing. This e to the iota alpha u, this should come here. E to the iota alpha u should come here. That's why it will become the Fourier transform of f. All right. Remark: the convolution is commutative. That is, f convolution with g is the same as g convolution with f. Since we know that this is the convolution, if you set x minus u equal to alpha, if x minus u is alpha, then u will become alpha x minus alpha. This u will become x minus alpha, and du is just d minus d alpha. All right. So this is what you got. Now from here, because the sign of the variable of integration changed, we have to change the signs of the limits of integration. You see, when u goes to minus infinity, alpha goes to plus infinity. So this integration is plus alpha to minus alpha. It's not minus infinity to plus infinity. It's plus infinity to minus infinity, and this minus will change it from minus to plus again. So again minus will be compensated, and you see this is the convolution of g with f. So this is the convolution of g with f. So this is commutative. It's very easy. Now, can we use Fourier transform to solve partial differential equations? We did use Laplace transformation to solve partial differential equations. Let's see how can we use Fourier transformation to solve partial differential equations. Let us consider the problem of flow of heat in an infinite medium, minus infinity to infinity, when the initial temperature distribution is known and no heat sources are present. Mathematically, this type of problem can be described in the following example. Because it's a one-dimensional heat flow, so we can write this one-dimensional heat equation from minus infinity to infinity, subject to the following boundary conditions. uxt and uxt both goes to 0 as x goes to infinity. All right. The boundary condition, because boundaries are not finite now. Boundaries are minus infinity and plus infinity. So I cannot have the values at plus minus infinity. But all we can say is that your ux and partial u by partial x, they both go to 0 as x goes to plus minus infinity. That your temperature far away will be 0. On the left side, the temperature far away will be 0, and there won't be any derivative of the temperature as well. Temperature will not be changing at that point. All right. So that's why the derivative is also 0. And the initial condition is, it's given, you see the initial temperature is f of x. So that is ux0 is f of x. So to solve this type of problem, because our domain is from minus infinity to infinity, Laplace transform only goes from 0 to infinity. So we need to use Fourier transform here because our domain is from minus infinity to plus infinity. Applying Fourier transform on the given diffusion equation, we get this thing because k is a constant, so Fourier transform of the second derivative and the Fourier transform of t. We know that Fourier transform of the second derivative is iota alpha square. So iota square will make it minus, and alpha square is inside, and Fourier transform of u is capital U alpha t. Here the derivatives come out. Partial by partial t will come out of the Fourier transform, and Fourier transform of u is capital U alpha t. So this becomes a first order ordinary differential equation basically. Right? This is an ODE subject to the initial conditions f. Now if you take the initial condition here, the initial condition is this. If you take the Fourier transform, this will give you Fourier transform at 0 and Fourier transform of f, which we may call capital F alpha. Alright, this is the initial condition. Now what is the general solution of this equation? Your auxiliary equation is m plus alpha square is equal to 0. So m is minus alpha square, so your answer is e to the minus alpha square t. So a is equal a e to the minus alpha square k t. There is k here as well in this green equation. You see alpha square k is also there. So using the initial condition at t is equal to 0, your a will come out to be f alpha. Alright, so your u alpha t will become a e to the minus alpha square kt, where a is f alpha. A is f alpha, this one. Alright, now if you take the inverse Fourier transform is right hand side is f alpha e to the iota e to the minus alpha square kt, this one. And to take inverse transform, I need to multiply by e to the iota alpha x with respect to d alpha. Alright, and the product form suggests the use of convolution because it's a product of two functions here, this and this, product of two functions, so I can use the convolution. If the Fourier transform of gx is e to the minus alpha square kt, then gx will be given by gx is equal to 1 over square root of 2 pi minus infinity to infinity e to the minus alpha x plus k alpha square t, which is exactly this one, d alpha. But we know that minus infinity to infinity e to the minus alpha square minus 2bx dx is this one. Alright, here a is equal to kt, b is equal to iota x by 2, therefore gx is given by this. In this formula, I replaced a by kt and b by iota x by 2. So if you replace, you will get this answer. This is your g of x. Alright, and now using the convolution theorem, your equation, this equation will take this form because one is f alpha, the other is the Laplace transform of Fourier transform of gx, so this becomes gx minus alpha. Now if you use the values here, you got this one, and now you got e to the minus x minus alpha square by 4 kt. We did it before as well. If you have this type of thing, you can replace x minus alpha divided by 4 kt, square root of that equal to some new variable. We call this z. Then the above equation will become e to the minus z square. That's it. This whole thing will become e to the minus z square. So this is what you got. Alright. So from here, if f is known to you, alright, you will be able to find the answer. Because this is your variable of that Gaussian distribution, e to the minus z square, but here f is being multiplied. We don't know the form of f because this thing is not given, initial condition is not given, u of x0 is f of x. So if fx is given to me, I will be able to find the answer. Otherwise, we will leave our answer in terms of integration. Alright? Because f is not known, so I cannot go further. Alright? So here, this was the first example of finding using Fourier transform to solve partial differential equations. Let's see another example. Solution of a diffusion equation in a semi-infinite medium. Semi-infinite medium means from 0 to infinity, not from minus infinity to infinity. So when it is from 0 to infinity, one condition at 0 will be given. Either ux0 at 0 will be given, or partial u by partial x will be given at x is equal to 0. And if you recall, in our sine and cosine transform, we said if u is given, we use Fourier sine transform. If partial u by partial x is given, we use Fourier cosine transform. Alright? So determine the temperature distribution in a semi-infinite medium x greater than or equal to 0 when the end x is equal to 0 is maintained at 0 temperature. Maintained at 0 temperature means u0t is equal to 0. So it means we will use sine transform, not the cosine one. And the initial temperature distribution is f of x. So let's solve this example. So that example is k times partial 2u by partial x square, because again it's a temperature distribution in a semi-infinite medium. So this is equation will remain the same. Now x is from 0 to infinity. Greater than or equal to 0 means 0 is less than infinity. It's a semi-infinite medium. T is of course greater than or equal to 0. Now your u at 0 is given. u0t is 0. Alright. And of course I will say that initial condition is u x0 is equal to f of x. This is given for t for x between 0 to infinity, and here for t greater than or equal to 0. So in addition, we will assume that also u and partial u by partial x, they vanish as x goes to plus infinity. This is the same condition which we had before, because far away as x goes to infinity, temperature should be 0 and it will not be changing over there with respect to x. Alright, so it means they both should go to 0 as x goes to infinity. It's a very reasonable physical condition imposed at infinity. So now if I take the Fourier transform of 1, we will get k times Fourier transform of Fourier cosine transform, Take Fourier sine transform of 1. Why sine transform? Because of this one. Right? This suggests Fourier sine transform. Alright? So from here we said if I take Fourier sine transform, partial 2u by partial x square with respect to alpha is equal to Fourier sine transform of partial u by partial t. This Fourier sine transform of second derivative was, if you recall, it was 2 by pi alpha u at 0t and minus alpha square of Fourier sine transform of u. Right? This was the left hand side. We proved it a few moments ago, right? We proved this thing equal to the derivative of Fourier sine transform. So let's say Fourier sine transform of u is capital U, then this is k square root of 2 by pi alpha. u0t is 0, it's given. Here you see u0t is 0 given, so this is gone. I'll get minus alpha square, let's call it capital U alpha t, is equal to partial by partial t of capital U alpha t. Alright? So by considering alpha as a parameter, you can write it du by dx. Alright? So du by dt plus k times, there is k as well, plus k alpha square u is equal to 0. Alright? So this implies that u alpha t is equal to constant times e to the minus alpha square k t. It's very similar to the one before. It's exact same equation. We got exact same answer. Now, one initial condition was given to me. If you want to differentiate between Fourier sine and Fourier transform and Fourier sine transform, you may write S with U as well. Let's say US is the sine transform of U. All right. But here, as we know that we are taking the sine transform, so you can just write capital U. It's fine. But if you want to write, let's say, a subscript S, that's fine as well. This just indicates that this is the Fourier sine transform of U. So when you take the inverse transform, you have to take the inverse sine transform. So it's just to remember for later when you take the inverse transform that this is not just the transform, it's a sine transform. Now initial condition was Ux0 is equal to Fx. So if I take the Fourier transform of this, Fourier sine transform of U, X0, Fourier sine transform of Fx. So you can write Us at X0 is equal to, let's call it Fs of alpha, that Fourier sine transform of capital F. All right, so this is your initial condition. So using this condition, we get US X0 is US alpha, sorry, not X. US alpha 0 will be A. This is A because e to the power 0 is 1, and that is Fs alpha. This implies your capital U alpha T is equal to Fs alpha e to the minus alpha square k t. All right. So this is your answer. Now you can take the inverse transform to find the solution uxt, small uxt. So take inverse Fourier sine transform to get inverse Fourier transform will give you your function back uxt, and inverse Fourier transform is 2 by pi 0 to infinity Fs alpha e to the minus alpha square kt, and what is inverse Fourier sine transform is sine alpha x d alpha. This will give you a function in x. Again, because Fs is not known, so we cannot go further. If Fs is known to us, then we may do something like this. But if you want to simplify your answer, you may write sine as the imaginary of e to the iota alpha x, and then you can combine e to the iota alpha x and e to the minus alpha square kt and simplify a little as we did in the previous example. But if you don't want to write it as e to the iota alpha x, then stop here, because if S alpha is not known, I cannot solve it any further. All right, so I got the solution in terms of integral form. All right. So if Fs is given to me, we will be able to further solve this integration and get the answer. All right, so we have solved these couple of partial differential equations, which were basically the diffusion or heat equations. One was in infinite medium from minus infinity to infinity, and the second one was in a semi-infinite medium from 0 to infinity. So say in a similar way, you can also solve wave equation and Laplace equation, which we have solved with the help of Laplace transformation as well as using the separation of variables method. So let's prove some properties of Fourier transform, which we studied in the beginning of the lecture. I'll solve a couple of properties and remaining can be proved. I will prove a couple of properties and remaining can be proved in a similar manner. Especially if you are given a higher order partial differential equation, let's say cubic equation, partial 3 or partial 4 u by partial x4, then taking sine and cosine transform, we don't know what type of expression we will get. All right, we have a general expression for Fourier transform, partial to n u by partial xn. So in a similar manner, you can prove sine and cosine terms and stuff like that. So these are basically the properties of Fourier transformation. So let's prove a couple of them, 2-3 properties, and see how we get these things basically. So first property was linearity, alright, that Fourier transform of C1 fx plus C2 f gx is equal to C1 Fourier transform of fx plus C2 Fourier transform of gx. Alright, this is what we need to prove. So to prove it, it's of course not difficult at all. Is equal to 1 over square root of 2 pi minus infinity to infinity C1f plus C2g with e to the minus iota alpha x dx. Right? This is your Fourier transform of C1f plus C2g. Now I can write C1fx e to the minus iota alpha x plus C2gx e to the minus iota alpha x and dx. Now because integration is linear, so I can take the integrations separately. So I can write 1 over 2 pi integration from C1 fx e to the minus iota alpha x dx plus minus infinity to infinity C2gx minus iota alpha x dx. Now C1 and C2 can be brought outside, so you can write C1 1 over square root of 2 pi minus infinity to infinity fx e to the minus iota alpha x dx plus C2 1 over square root of 2 pi minus infinity to infinity gx e to the minus iota alpha x dx. Now this is Fourier transform of f and this is Fourier transform of g. So what you got, C1 Fourier transform of fx plus C2 Fourier transform of gx. You see, it is proved. It's proved the linearity property. It's very easy. So basically we use the linearity of the integration to prove the linearity of the Fourier transform, as was the case with Laplace transform. Second was the scaling, right? Scaling property, that f of Fourier transform of f alpha x or ax instead of using alpha, because alpha is used in, so that is 1 over a f of alpha over a. If f is a Fourier transform of small f, this is what we need. So to prove this, I can write Fourier transform of f ax is equal to 1 over 2 pi minus infinity to infinity f ax e to the minus iota alpha x dx. It is alpha, not minus alpha. Minus alpha comes in the inverse transform. So this is also plus alpha, plus alpha, plus alpha, plus, 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 plus. All right. Plus alpha, plus iota alpha x comes in the Fourier transform, minus iota alpha x in the inverse Fourier transform. So if this is your Fourier transform of f ax, then what you can do is you can set ax is equal to t. This implies that x is equal to t by a. All right, and dx will be 1 over a dt. As x goes to minus infinity, t goes to minus infinity, and as x goes to plus infinity, t goes to plus infinity. So limits are not changed. So Fourier transform of f ax becomes Fourier transform of f a becomes minus 1 over square root of 2 pi minus infinity to infinity. This becomes f of t, and e to the iota alpha x becomes t by a, and this is dt by a. Now you can bring this outside, 1 over a outside, so this will become 1 over a square root of 2 pi iota alpha t, here it is a. So I can write iota alpha by a t dt. So what is the difference in the Fourier transform here? Only difference is that your alpha is replaced by alpha by a. So this is the Fourier transform with 1 over a. This inside thing is the Fourier transform of f, same f function, but now our argument is not just alpha, it is alpha by a. You see, from here it becomes alpha by a. Alright, so see, scaling property is again simple. Similarly, you can prove different properties, differentiation properties, other shifting property, which is fx minus alpha. They are easy. On the same steps you can prove that thing. Let me prove that the derivative one, right? We had an example, the derivative Fourier transform of the orth derivative of x gives you minus iota alpha or and Fourier transform of fx alpha. Let's prove this one, right? So Fourier transform of this left hand side, the orth derivative with respect to alpha is 1 over 2 pi minus infinity to infinity f r x e to the iota alpha x dx. Alright, so again I can use the integration by parts. So I can keep e to the iota alpha x as it is. Integral of fr is fr minus 1x from minus infinity to infinity. Minus infinity to infinity. The derivative is iota alpha e to the iota alpha x, and integral is fr minus 1 x dx. And we had a condition here that all derivatives up to r minus 1, f and its derivative up to r minus 1 will vanish as x goes to plus minus infinity. So this thing will become 0 as x goes to infinity and x goes. So as fr minus 1 x goes to 0 as x goes to plus and minus infinity, so this first term drops out. First term drops out, it becomes 0 minus iota alpha minus infinity to plus infinity e to the iota alpha x fr minus 1 dx. This is what you got. Now you got minus iota alpha 1 over square root of 2 pi minus infinity to infinity e to the iota alpha x fr minus 1 x dx. Now this is the Laplace, this is the Fourier transform of fr minus 1. So what you got is Fourier transform of fr x is minus iota alpha Fourier transform of fr minus 1 x. This is what you got. So now if I use exact same expression for fr minus 1, it will give me minus iota alpha Fourier transform of fr minus 2 x, right? If I replace r with r minus 1, I get minus iota alpha r minus 2. So I got minus iota alpha square f r minus 2 x. Again fr minus 2, by using again same expression, I'll get minus iota alpha Fourier transform of fr minus 3 x. Means if I replace r by r minus 2, I'll get r minus 3 here. So now the answer is minus iota alpha cube fr minus 3x. So see, if I replace r with r minus 3, it gets me cube. R with r minus 2 gets me r square. If I carry on in this manner, okay, what I will get is minus iota alpha to the power n and Fourier transform of, sorry, not n, r and r minus r x. And r minus r means no derivative. f0 means no derivative, f as it is. Alright, so f of frx becomes minus iota alpha r. Alright, so using this, basically we proved using this with f(x) is equal to u xt, we have, I used it directly, I used this formula. I said if we have partial and r is equal to n, partial nu by partial x n will become minus iota alpha n, and the Fourier transform of u xt with alpha. All right, so this is what we used, and I can use it by replacing f with u and r with n. I got this one. You can prove this directly if you want by using this integration by parts. Just use integration by parts 1. You will get partial n by partial x n is equal to minus iota alpha, partial n minus 1 by partial x n minus 1. Now using this relation recursively, you will end up getting minus iota alpha to the power n Fourier transform of u xt only, because n minus n will give you no derivative of u, it means u itself. All right, so that's how we can prove different properties of Fourier transform. I left couple of properties by using the definition of Fourier transform, you can prove them very easily. Thank you very much for being with me for today's lecture. I will see you in the next lecture. Till then, Allah Hafiz. Assalamu alaikum.